EDX Decision 1, Graphs and Networks 1, Definitions and Spanning Trees. Finding the minimum spanning tree using Kruskal's algorithm. We've already seen Prim's algorithm for finding a minimum spanning tree. Think about how you would solve this problem in your head. If you're faced with this problem, you might just look for the shortest edge. So you might want to start off with this 6 as being the shortest edge. And then you might move on to the next shortest edge, which is the 8. So what you might do first is look for the shortest edge and then the next shortest edge, etc. But you must avoid creating a cycle. So which edges would we choose and why? And this is formalised in Kruskal's algorithm. So Kruskal first published this algorithm in 1956. So his algorithm states, select the shortest edge in a network, select the next shortest edge which does not create a cycle, repeat step 2 until all the nodes have been connected. So Kruskal is another example of a greedy algorithm. It looks for immediate benefits, and we must always list the edges in the order that they have been selected. So here we go. So find the shortest edge, which in this question is the 5. So that's WL 5. Find the next shortest edge in this network, which is the 7. So we've used CL at 7. The next shortest edge is 8, but we can't use 8 because that would create a cycle. So we move on to the next shortest edge, which is over here at 11. So that's SR at 11. The next shortest edge is one of these two 12s. You can choose whichever one you want to use. So I'm going to choose this one here. So I'm going to use CR at 12. So at that point, I've connected all the nodes together, and the total is 20, 35. So my minimum spanning tree is 35 units long. Applying Kruskal's algorithm to this slightly more complicated network, the shortest edge on the diagram is the 18. So that's DE at 18. The next shortest edge is GF at 21. So I include GF at 21. The next shortest edge is CD at 22. So I'd use that edge. CD 22. The next shortest edge is BD at 24. There are actually two 24s. I can't use this 24 because that would create a little cycle. So I have to use BD at 24. The next shortest one is EG at 26. And the next shortest one is AC at 30. I can't use the 29 by the way because that would create a cycle here. So you skip over the 29 and the next one I can use is the 30. AC at 30, and then I can't use 31 because that would create a cycle, so I'm going to use the 33. HG at 33, and that has connected all the nodes together in a minimum spanning tree. And the total for this minimum spanning tree is 174, which is the same solution you would get with Prim's algorithm. Kruskals cannot be used in a matrix tabular form, and you need to be able to understand why. Prim's algorithm, which relies on selecting nodes and comparing the nearest neighbour to those nodes, is far easier to do in a tabular form. Kruskal, which is looking for shortest edges which are not connected with, would be extremely difficult to implement in a tabular form. Some of the common errors with this method: not choosing the next shortest edge to add to the solution, accidentally creating a cycle so the solution is wrong and it is not a tree anymore, not selecting from all the available edges when looking for the next shortest edge, and forgetting to record the order of the edges as you go along, and forgetting to state the length or the weight of the minimum spanning tree as your solution. So finally, just comparing Prim with Kruskal. Both algorithms are greedy algorithms and find an optimum minimum spanning tree, but the edges will be added in a different order depending on the algorithm. If there is more than one minimum spanning tree, the two algorithms may find a different minimum spanning tree, but it will have the same value. Prim's always joins a new node to an old node so that every stage is a tree, whereas Kruskal allows both new to new node connections and old to old node connections to be made, so there is a risk of creating a cycle, and we must always check for cycles when doing Kruskal's algorithm. Kruskal's algorithm cannot be used in a matrix tabular form. Thus, whilst it is good for small networks, it is not easy to program for a computer to deal with larger networks. So for larger, more complicated networks, we would be looking at using Prim in a tabular form. And that brings us to the end of Graphs and Networks 1.